Welcome to video 8 on the TTb course. This video is from part 2 of the TTb course. In part 2, from video 3 to video 10, we consider various techniques that form the foundation of reliable TT systems. In this video, we consider some crucial definitions. We consider what we mean by a state, what we mean by a mode, and what we mean by a submode. It's important that you are clear about what these terms mean, because we'll be using them throughout the remainder of this course. The material in this video is based on ERES 2, Chapter 8. I always ask that you read the book chapters before watching the video. In this case, it's particularly important. You may need to watch this video a couple of times to be clear about the meaning of these key terms. It will be much easier for you if you read Chapter 8 of the ERES 2 book before watching this video. Everything should make more sense if you do it in that way. So I'd ask please that if you haven't read Chapter 8 of the book, please do that now before watching this video. So let's start with these key definitions. So the definitions that I'm going to talk about here are taken from the ERES 2 book, Appendix 1. You may like to take a look at the definitions as they are presented on the video, go back, have a look at the book, then come back and continue with the video once you're clear about the various definitions that are used here. Let's start by the meaning of state. In many cases, in many books, it's difficult to distinguish between what's meant by a state and what's meant by a mode. Here, in this course, we've tried to be clear about the distinction. When we're talking about a state, we mean a software configuration on a processor where there's no scheduler running and no tasks are being released. That's the key factor here. So when we're talking about a state, we mean a software configuration on a processor in which no scheduler is running and no tasks are being released. So a state is often employed when the processor is performing low-level startup tests, when a multiprocessor design is synchronizing the activity on different processors, and in fail-safe processor states. So a state means a software configuration on a processor in which no scheduler is running and no tasks are being released. In practical designs, states are often implemented to top and tail the system operation. In other words, we may implement a state in order to perform low-level startup tests on a processor before the scheduler begins to operate. We may use a state to synchronize the activity on different processors as a multiprocessor design is configured, a process that may involve the use of wait-safe processor states. You might like to look up wait-safe processor state in Appendix 1 of the ERES 2 book. The third way in which we use states is typically to implement fail-safe behavior on a given processor after the scheduler is shut down, if a problem occurs during the processor or system operation. So, to reiterate, a state means a software configuration on a processor in which no scheduler is running and no tasks are being released. We typically use states to implement processor behavior at the beginning of the system operation, low-level startup tests, synchronization activities, and when a processor is being shut down, to implement fail-safe behavior. Those are the key uses of states on this course. A mode means something different. A mode means a software configuration on a given processor that involves the release by the scheduler of a named set of periodic tasks in accordance with a predetermined schedule. In practice, during normal operation, the kind of TT systems that we're considering on this course may be operating in one of a number of different processor modes. When we change the mode, this means either that we're changing the tasks in the set, so we're moving from one task set to another task set, or we're keeping the same set of tasks, but we're changing the parameters of one or more of the tasks. Let's look at a simple example first. So this aircraft is operating in a number of different modes. So we have one task set at this point in the system operation when the aircraft is rising to its cruising height. So we have one task set A, C, B, D here. Then when the plane's at cruising height, we're running a different task set, PRQS. And in the final mode that's considered in this diagram, while the plane is coming into land, we're running this a further task set, WXYZ task set when the aircraft is coming into land. So we have different modes, different processor software modes, different modes that we usually refer to them as, and each of these modes we're running a different task set. More formally, task set X and task set Y and task set Z below are all different. If you consider task set Y and task set Z, the difference between these task sets is straightforward. In task set Y, we're running task A, task B, and task C. In task set Z, we're running task set D, task B, and task C. Different tasks, it's clear that the task set is different. Task set X and task set Y are also formally different. Here we have the tasks A, B, and C running in each task set, but the task period here for C is 5 milliseconds and here for C is 7 milliseconds. Because the task parameters are different, these are formally different task sets. So the task sets are considered to be different if the tasks themselves vary, as in this case, or if the parameters of one or more of the tasks are varied, such as the task period. If we vary the task period, then formally we're changing the task set. And if we're running this task set or this task set, we would change mode to run task set X, task set Y, and task set Z in the types of designs that we're considering on this course. So in general, we have the ability to change mode at any time. This mode change may, for example, be triggered by user inputs or by changes to the environment. This is a key way in which we make our system flexible. People sometimes think that time-triggered designs are inflexible because they're always performing the same tasks in the same sequence. That's not the case. We can change mode at any time, often very quickly in response to user inputs or changes to the environment. The difference is that within each mode, we retain the advantages of a TT design. Because within any particular mode, the tasks are released according to a schedule that can be reviewed, validated, and verified at design time, when the system is developed. So we know that we're running in a particular mode. We know all of the possible system modes for the system in advance, and we check and verify each of those system modes. Then at runtime, we can change between modes depending on the environmental situation and on inputs from the user. The final key term that we need to understand here is submode. So a submode means a subsidiary processor software mode, a subsidiary mode that is used to help structure the system design. Within a given mode, the processor may be viewed as operating in one of n different processor submodes. Submode is usually represented by a subset of the task state of the processor task that is operating in a given mode. What this means in practice is that the processor submode is usually represented by means of a combination of a static variable and a switch statement in the processor task. There are lots of defined terms shown in this slide. Each of the terms here that's in small capitals is defined and laid out and explained in Appendix 1 of the ERES2 book. You may like to pause the video at this point and look up the various terms that are defined here to make sure that you understand what's being presented. So I understand that this may appear rather complicated, but it's important when working with these kinds of systems to be absolutely clear about what we mean. It's impossible to create a reliable system if the requirements are unclear. So we've tried to be clear here about exactly what each of these terms mean. Each of these terms has a formal definition in Appendix 1 in the ERES2 book. You may like to pause the video now and be clear and look up each of these terms to be sure that you're clear about what each of them means. Here's an example of the use of modes and submodes. So here we have a simple traffic light system. These are the possible submodes. So we're assuming that within the normal mode, the traffic lights may either be in a red state, red and amber, a red submode, a red and amber submode, a green submode, and an amber submode. So while the system is operating normally, these are the valid submodes. These are the valid light configurations that we can expect from our traffic lights. If a fault is detected, we're assuming there's only one valid submode here, and that in that valid submode, all of the traffic lights will flash simultaneously to indicate that something is amiss with the system. So we might have some startup states that are not shown on this diagram. Having completed those startup states and gone through some startup tests, we would enter normal mode. Within normal mode, we have 4 valid submodes that we may enter. If we detect a fault in this system, we go into fault mode. Within fault mode, we've only got one submode. In that submode, all the bulbs are flashing. So how do we implement effective multi-mode designs? If we're to develop reliable multi-mode TT designs, we need to handle the transition between modes with care. The way that we approach that in this course is that we usually change the mode by means of a processor reset. Use of a reset-based mode change helps to ensure that the transition is made between one set of tasks that has been subject to detailed analysis, test and verification at design time, and another set of tasks that has been similarly checked at design time. It also ensures that we can clean up between the task sets. It's possible to change modes without requiring a reset. We consider this option in the ERES2 book in Chapter 8. But in the great majority of the examples that we look at on this course, we're going to use reset-based mode changes to make the transition between one set of tasks and another set of tasks. And I recommend that you use a reset-based mode change wherever this is possible on your designs. Is laid out on slide 14 here. So in the majority of multi-mode designs considered in this book, we use reset variables to store information that is required after the system reset. Most modern MCUs have access to a number of registers that are designed to retain their contents when the processor is reset, provided that the power supply is maintained. This is what we require to support reset variables. Here's an example of such a register set from an STM32F4 processor. These are some backup registers that can be used to store information between processor resets. And some of the code examples that we refer to during this course make use of such backup registers. Sometimes we need to go from a normal mode to a fail-safe state. In the presence of some abnormal processor states, it may be necessary to move the system into a fail-safe state until the platform is switched off. At this point, it may also be appropriate to prevent the platform from being started or activated again until it has been reviewed by a suitably qualified individual, either in person or in some cases via a remote diagnostic system. We may leave the user or others at significant risk if we force the platform into a fail-safe state immediately when an abnormal processor state is detected. One way we can deal with this is to provide a limp home platform mode at least as a first option. So we might have a number of normal processor states, and while the system is operating correctly, without faults, we may change between these different normal operating modes. If a problem is detected, we may go initially into a limp home operating mode, and if further problems are detected, we may then enter a fail-safe state. So in our normal modes and our limp home mode, we'll be running the scheduler and running some task sets typically. And in the fail-safe state, we will not usually be running the scheduler. We will usually be simply running a very simple function, possibly in a superloop configuration. Same mode resets are also something that we need to consider. So when we're thinking about what we might do in the presence of an abnormal processor state, we can also consider performing a same mode reset. This involves resetting the processor and starting it up again in the same, usually normal, mode. If the problem is transitory, this can often be an effective solution. It's easily achieved using the frameworks presented in ERS2 Chapter 8. Note that we may need to implement an appropriate mechanism to ensure that the processor does not perform an endless series of same mode resets in the presence of sustained EMI, for example. So the first thing we might want to consider doing if we detect a problem in our system is performing a same mode reset to see whether that will deal with the problems that have resulted in the system. Same mode resets and examples of these are presented in the ERST book in Chapter 8. So sometimes we want to perform same mode resets when we detect a problem with the given processor or a given platform. It can also make sense to perform same mode resets when we're in a normal processor state. Such an approach is sometimes followed in designs that must operate in high radiation environments. Here, the system may be designed to reset every few minutes, even where no faults have been detected, in order to reduce the likelihood that single event upsets will disrupt the system behavior. That can be good use for same mode resets. Same mode resets are also employed in some single processor designs that rely on a watchdog timer as a means of detecting and handling failure of the scheduler. We say more about this in video 16. So we sometimes perform save mode resets as a means of performing built-in self-tests, periodic self-tests of key components or units or mechanisms in the system. So sometimes we use save mode resets to perform tests on parts of the system. We'll say more about this in video 16. How can we support submodes? Within a particular mode, the processor may operate in several different submodes. Transition between the submodes may depend on the passage of time and or on inputs. So, autopilot systems, industrial robots, traffic lights, automatic washing machines, etc. There are lots of possible applications for different submodes in our design. We looked at a traffic light example in an earlier slide. Let's just look at one way in which we might be able to implement that example. So this example is taken from the book Embedded C. We have 4 submodes in the design. Red, we stay in this submode for 20 seconds. Red and amber, we stay in this submode for 5 seconds. Green, we stay in this submode for 30 seconds. Amber, we stay in this submode for 5 seconds. There are no inputs to the system in this simple example. So we are storing the time in each of our 4 possible submodes using hash defines. We've got a user-defined type for storing the light submode in our system. That brings us to the end of this video. Please read Chapter 9 in the ERES2 book before you watch the next video. Thank you for watching this video.